Hello, we are group number 17. Jimmy has giant nose. My name is Jet Tsai, and I'm going to introduce our experiment, which is damped oscillation, aka 阻尼震荡 in Chinese. First, let's talk about the equipment we are going to use. And the first one is aluminum plate. This is for creating the eddy current on it. The reason why we don't use iron plate or other metal is because we don't want the magnetic force too strong, or the magnets will stick on the plate. And next equipment is bracket, and just for putting the pendulum on it. And the long ruler and magnet construct the pendulum we need. The reason why we don't use cord is because we don't want the magnet stick to the plate, so we use ruler instead. And next one is graph paper, just for graphing. And we will need camera or mobile phone to record the whole process of the experiment. And the last one is tracker. It is a software to track the position of the magnet. Therefore, we can analyze the relation between time and position or angle of the magnet. So here is the picture of the erection equipment. And next, I'm going to talk about the whole process. So first, we raise the pendulum, the magnet, to the proper height. And while we release it, uh, it will uh, 产生什么? It will constantly create the eddy current on the aluminum plate against the direction of the velocity, which slow down the pendulum. So it will continue influence. So the velocity will get slower and slower. That's it. And next we will introduce Jimmy Shang to uh, to talk about the principle behind this experiment.
Okay, I'm gonna talk about the principle of this experiment. And first, let's imagine a single pendulum, which means 单摆 in Chinese. So, first, we have to have the concept of inertia, which is 惯性. And that means that all the things that move in fixed world will keep moving. Yeah, so if we are talking about the single pendulum system, it should work like this. It will keep moving, moving, moving. Yeah, but there's the gravity. So actually, it doesn't move this way. It moves in a like this. Yeah, and uh, the problem is that in a not ideally world, there's actually other forces that influence to this pendulum system, and for that, we have to talk about the another concept, which is damping, which is 阻尼 in Chinese. And we can actually imagine it as like the pendulum is moving in a, let's say, glue. So as you can imagine, if this thing is in the glue, yeah, and the glue will try to move this system slowly down. So maybe like this. Okay, and however, what makes this slow down in a single way is that the friction that is caused by the air. But the cost of the air is actually pretty small, so it may not be a good way to create damping. Um, and what we do in this experiment is that we use a aluminum plate, and the plate will create a kind of current called eddy current, which is 涡电流. And that means that you can imagine the plate as infinite uh, circles of metal. And as we know, if a magnet is trying to move forward or move away from a circle, a metal circle, the circle will create currents, which is eddy currents. And you can imagine it as if a magnet is moving to the circle, and there's like a another ways magnet that is trying to defeat it. And if the magnet is moving away from the circuit, and there's a magnet that's trying to bring it back. So, in conclusion, the force of any current is just like a very strong force that will try to stop the magnet, which is the small ball in the pendulum system, to move. And by that, we create a damping system. And also, the damping is related to the velocity, because the faster the magnet move, the force of the eddy current will be stronger. So the velocity is related to the damping, and the velocity is also related to the place of the small ball, the magnet, and it's also related to the angle of the system. So by that, we can create a math relation between the angle or the place of the magnet and the time.
Hi. This is a part of an animation of the simulation. And we can see this black bar is ruler, and the gray circle is a magnet, and the blue bar is the aluminum sheet, and it's behind the magnet with some distance, like 3 or 4 or 5 or 12 millimeter. And first, we want to pick the magnet at the proper height, and then it will start dropping. And when it dropping, the aluminum sheet will induce some interclockwise eddy current. Yes. And when the magnet is not near the aluminum sheet, the it will induce some clockwise eddy current. And we can see when the magnet when the velocity of the magnet is zero, it's lower than before. And when it start dropping, it will induce some interclockwise eddy current. And this process will continue until the velocity is zero and the magnet is not moving anymore. So we want to use Python to draw the graph of the position depend on the time, and use some parameter like the weight of the ruler, the weight of the magnet, and the centroid of the ruler and the magnet, and some gravity and some critical damping value. So our goal is to this simulation will classify our experiment is correct or not. So yes, and this is our yes, this is the end of this part. Thank you, and this is my picture. Thank you.
Next, I'm going to introduce the analyzing tool. This app is called Tracker. It can use in tracking movement of objects. First, we we have to download it from the website, and after install it on your computer, you can open the experience video from here, and you can choose the video you want. And then we have to set a standard ruler. Check this button, and here we can change the length of the ruler. And here I'm going to have 1 centimeter long. And we can also select the starting point and the end point. So this is our standard ruler, and we have to select the XY axis. We can also change the angle of the axis, but here we just select in a simple way. Okay. Or you can just change the angle from here, 0. Now we have to select a checking point while analyzing it. Press Shift and check the point you want, and you can get 1 data point, like this. Like doing this, and you can get several data points. Or you can press Shift and Control in the same tab, and the app will automatically find the point. But at least there's no similar point in this red block. But you can see that the quality of video is bad, so it can't find the correct point. So I have to select the data point myself. Okay, then after you select a couple of data points, you can get a graph, and you can change the type of the graph, like you have V and A, or some other kinds of graph. Okay, then no, that is one. Or we can also output the data from the app, and you can input it to Python or anywhere you want to analyze this data. So this is Tracker, the app we're going to use during our project.
The next part is to analyze the difference between undamped and damped oscillation. It will mainly introduce the theoretical formulas and then verify it with experimental data. Okay, let's start with analysis of undamped oscillation. Oscillation of an elastic body without external force is called natural oscillation, and its corresponding frequency is the natural frequency. The left formula shows a method of how to calculate the natural frequency. The formula on the right is another method to calculate the natural frequency with more parameters. Next are the experimental results of our experiment. It can be seen that the oscillation is very stable without damping.
We also compare the two formulas just mentioned and what is the difference between our experiment result. For the formula on the left, our calculation method is like this. The period of undamped pendulum is 1.18 and the natural frequency omega is calculated to be 5.32. For the formula on the right, our calculation method is like this. The ruler weighs 82.8 g. The magnet weighs 51.5 g. And the center of mass is 35.2 centimeters. From the axis on the rotation, omega is calculated to be 5.11. Finally, we calculate the error between the two. The error fell to 4.1%. Okay, let's turn to part 2 analysis of damping oscillation. As mentioned by the previous part, there are three types of resistance: overdamping, critical damping, and underdamping. The picture on the left shows the results of the three types of damping on the XT diagram. The red line is underdamping, the blue line is critical damping, and the yellow line is overdamping. The three formulas on the right are the solution of the natural frequencies under the three damping conditions. Next, this is the experimental results of our experiments under damping conditions. We changed total of 8 different distance as operation variable to carry out the experiment, and finally got this picture. It can be seen that the highest value appears in the parameter of 12 micrometer. Next is our experimental results of changing the y-axis to angle, and finally got this picture. We can also find the highest value appears in the parameter of 12 micrometer. Finally, we perform linear regression from the previous experiment, and then we can get the damping coefficient. The damping coefficient obtained by our experiment is 0.9295. And the above is an analysis of undamped and damping oscillation.